Okay, folks, welcome to today. Don't forget, this afternoon's a little bit kind of messed up. Well, no, this afternoon's not. I have a Clemson Calculus Challenge meeting at 11, so I won't be in my office from 11 to 12. I anticipate I should be back in by then the front. So, but I'll be in my office as usual from 12 to 2. Okay, so the last thing we were talking about was this. So there's a couple of things that we say I'm going to remind you what the sum of two ideals are. This is just practical stuff. Alpha plus beta, but alpha's an I. It's easy to verify this ideal. If I plus j, that ideal is the whole ring. And another way to put this, here's a simple way to put this, since we're talking about rings of identity. We say that I and j are comaximal if I plus j has 1 in it. That's all you need. So in other words, there's something in I plus something in j that add up to be 1. So that's kind of an easy way to think about it. Theorem 1718. First isomorphism theorem. Now here's kind of a good thing about these kind of mathematics. This is going to look almost exactly like the first isomorphism theorem proves. So suppose the phi from R to T is, instead of a group homomorphism, now we're talking about a ring homomorphism. Then there is an isomorphism of rings. Notice this statement is exactly what group theory. R mod the kernel is isomorphic to the image given by your input is a coset here, and your output let me sketch this. I'll probably go through all 40 details because this is almost exactly like the first isomorphism there. Here's actually it's a little bit easier because rings are big groups. As is usual in this kind of proof or sketch here. The heavy lifting is actually showing that this B bar is actually a function. The rest of the other algebraic properties of this are actually pretty easy. Remember what I mean by this. Your input here, this is actually a coset, right? So this could consist of infinitely many elements, right? And you picked one, R, to plug in. I might have picked something a little bit different to plug in. We better get the same answer. So So suppose that R plus curve phi is R prime plus curve phi. So you elected R to represent this coset. I elected R prime. This means that the difference of those two is in the kernel, right? That's what it means for them to come out of that single coset. So, E of R minus R prime is 0, right? Because this guy's in the kernel. It's like being in the null space below your transform. It kills it. But nothing up my sleeve. This is phi of R minus phi R prime. There's the homomorphism. And so this means phi of R is phi of R prime. Therefore, phi of R and that's it. The rest of the proof is very much like the proof for the first isomorphism of general groups. I'll let you look that over and see if you've got any problems with it. Any questions? Okay, let me give you a theorem that we've seen before, only I did it a little bit differently the first time, and also in the previous homework. We had the Chinese remainder theorem, and I set that up as a system of congruences, right? And these congruences have some solution that's unique in this range. Here's another way to couch this. And I'll show you why, when I've done this theorem, why you would care, why you would want to do this. Remainder theorem. Second version. This is just stated in a different way. But I want I2 all the way up to IK the ideals of R, and the function F given by again. In fact, we always want to do the easy thing, or the easiest thing possible. What's the easiest function I can think of? Okay, what do I need? I need a K tuple. Right? My input is R, and in the first thing I need an element of this quotient. Well, the easiest thing I can think of is the coset R plus I1. The easiest thing I can think of is R plus I2. Just repeat this all the way across the board. This is a ring homomorphism. With a kernel, I'm not gonna write down the kernel. I bet you can guess. Can anybody guess what the kernel of this function is? let me recall for you the identity of this direct product of rings is 0 plus I1, 0 plus I2, 0 plus IK, blah, blah, blah. What does it take for an element R to be in the kernel? What does it take for every coordinate of that to be the 0 percent? Well, let's just take this one step at a time. For me to be 0 across the board, I've got to be 0 there first. What does it mean for R to be the 0 element of this? R plus IK equals 0 plus IK, or I'm sorry, R plus I1 is 0 plus I1. What does that mean about R? That's too good. That's too specific. Yes, 0 works, but it works more general.
The difference equals 0.
There you go. What it means for R, scratch here. This is equivalent to saying that R is in I1. So any R in I. So what do I need to make that first coordinate 0? I need R to be in I1. What do you suppose I need to make the second coordinate 0? R has to be in I2, right? To make the third, R has to be in I3, and so forth and so on. So what do you suppose the kernel is? What does it take to go 0 all the way across the board? It has to live, R has to live in all of them, right? So the kernel of this should be and by the way, Coleman, your first answer was 0, but 0 is contained in all of this. So that's going to work, right? But maybe, just maybe, there's more. If pairwise maximal if these ideals are pairwise maximal, then I1 intersect I2 intersect IK is actually the ideal I1 I2 IK. And in this case, R mod I1 I2 IK is isomorphic to R mod I1, R mod I2, R mod I2. Okay, this looks maybe a little bit abstract. And why would we care about this? Let me give you an application. And I mentioned this last time. What R equals C? Suppose in the setup for the Chinese remainder theorem, let's just I1 be P1 to A1, P2 to A2. So remember, every ideal in C is generated by some element. So I'm just making these prime powers. Now, what's kind of nifty about this, and you can also assume that my exponents are at least 1. Notice that these ideals are pairwise comaximal, right? Because what's the greatest common divisor of P1 to the A1 and P2 to the A2, for example, it's 1, right? Because they've got no prime in common. That means the GCD is 1. There's a linear combination of those two that's equal to 1. Remember, once again, we go back to these basic properties of the integers. That means that these two ideals, and in fact, any pair of distinct ideals are comaximal because there's linear combinations of stuff in the ideal that's 1. I agree with that. The Chinese remainder theorem that Z mod the product of these ideals is isomorphic to that's what the Chinese remainder theorem says, is I can break up this product into these pieces.
So writing it out like C divided by P1.
Oh, you know what? I'm super sloppy. I should have put another Z here. And let me write this another way for you. This notation that we use is C P1 A1, C P2 A2. Is that a little bit more familiar? So let me give you an application. Let's go. Nobody wants to write down 2,940 integers and check to see if they're relatively prime, right? Notice that this is, if I got this right, well, 60. The Chinese remainder theorem allows me to break this up, this big, huge mess, into digestible chunks. And not only does this allow us to count efficiently, but this also allows us to, from this perspective, actually describe what the units and the nilpoints and zero values. Let me ask you this. How many units are there? And I am going to not put the bars over the numbers here just to save trouble. How many units are there in Z4? That's exactly right. And if you don't remember, you can always do the Euler phi function. In fact, you can do the whole Euler phi function on 2940 as well. But this would be 1 times 2, which is 2. And the units are 1 bar and 3 bar. C12, I'm sorry, C3.
How's that formula work again?
Oh, well, it's multiplicative across primes, but times prime, everything's a unit except for 0 bar element. 49 is a little bit more complicated. I'm not going to write this out, but it's everything that's not divisible by 7, right? So it's everything but 0 bar, 7 bar, 14, 28, 21, 35. And, well, I got that there. It's everything but. So number of units. How do we count these? Well, to be a unit in this thing, notice the identity of this thing is 1, 1, 1, 1, right? So to be a unit, you've got to have a unit in every coordinate. Everybody agree with that? So the total number of units should be, you have 2 choices for your first coordinate, 2 choices for your second coordinate, 4 choices for your third coordinate, and 42 choices for your fourth coordinate when you decompose it this way. So this is something like, what is this? 168, that's 336, and so that's 6, 7. Yes.
I think when they like overlap though, it's like why can you count like 1 in Z4 and 1 in Z3 and 1?
They don't overlap, and that's the beauty of it, because they're all separate coordinates. And actually, the one here is a 1 bar mod 4, and the one here is a 1 bar mod 3, which is actually different, right? And that's actually put your finger on what makes this a powerful theorem and what makes the counting easy. So there's 672 units. Everybody agree with that? You can count the 0 by the way, this, you can construe this as a proof, as I promised earlier, the fact that the Euler phi function on p to the n worked that way, this the Euler phi function decomposes this way. The Chinese remainder theorem shows this, because to be a unit, you have to be a unit in every coordinate. And that's exactly the decomposition earlier from the Euler phi function. 0 divisors.
Is there no overlap because they're all prime? Like it's 2, 3, 5.
They're all relatively prime, and that's the important thing. And in fact, another thing I could have done is I could have decomposed this into Z12 and then Z 5 times 49, because those are co-maximal as well, as long as they're relatively prime. But I like to break it up into prime powers because they're the easiest to kind of wrap your head around. 0 divisors.
you can only use like the phi formula with primes, right?
Yes, the Euler phi function is defined on primes, and then to do it on n, you break it up over the primes. The zero divisors is 2940 minus 672 equals 868. Oh, no. By the way, can you characterize what it means to be a zero divisor? You can count these by hand. You can double check yourself. To be a unit, you have to be a unit in every coordinate because you have to multiply something in those four coordinates to get 1, 1, 1, 1. That means that every entry has to be a unit. What do you suppose it means to be a zero divisor? Right. That's sort of this. Not a unit in at least one coordinate. Because if there's one coordinate you can't invert, then you're totally hosed, right? So if you're not a unit, and of course that's a little bit harder to count, right? Because there's different possibilities. So it's easier to count the units and subtract off, right? What do you suppose it takes to be a nilpotent? That's right. That's right. The nilpotents not a unit in every coordinate. By the way, let's count the nilpotents then, shall we? How many non-units are there in C4? Correct. 0 bar and 2 bar. In Z3, there's only 1. In Z5, there's only 1. Because 3 and 5 are prime, so the only non-units is 0. Are you guys okay, or if I completely?
No. I was just trying to.
Okay. 42 of those guys were units, so I guess that leaves what, 7 here. So there should be 14 nilpotents. And notice another way that we thought about this before is to be a nilpotent, it has to pick up every single prime factor. So to be a nilpotent, it has to be a multiple of 2 times 3 times 5 times 7. So that has to be a multiple of 210, right? And 210 times 14 that's another way to look at it, but there should be 14 nilpotents. So summary, 672 units, 2,268 zero divisors, of which 14 of them are actually nilpotent. Everybody okay with that? I hope that you all can appreciate a little bit of the power of this, because back in the day, just a few weeks ago, I mean, you would have burned me in effigy for asking you this question, right? Because nobody wants to write down 2,940 things and go through and check that graph, right? But the Chinese remainder theorem makes this really doable very quickly. Okay, any questions? Okay, so I am going to outline how the Chinese remainder theorem works from this point of view. And I'm going to do the hard case. I'm going to do the case for 2 ideas. And I'm going to leave the rest to you because everything else is induction after that. So Well, actually, I'm going to proof. T. Supposed to be an F bar is R plus I1, R plus I2, R plus I10. I will briefly show that this is a homomorphism. Well, because of the way that direct products and co-substitution works, this is R1 plus I1, R1 plus I2, R1 plus I2, R2 plus I1, R2 plus I2, R2 plus I2. Right? Because if you put this back together, this is R1 plus R2, I1, R1 plus R2, I2. And this is F of R1, F2. So it's a homomorphism additively. What about multiplicatively? Let me write it XY. So I should have written it XY in the perfect place. Make it a little easier. This is XY plus I1, XY plus I2, XY plus I10. And this is X plus I1, X plus I2, X plus I10 becomes Y plus I1, Y plus I2, Y plus I10. Again, I'll sort of argue backwards because if you put this back together, it's the product of these, which is that. The second part of the product of these, which is that, and so forth. And this is F of X. So this is a homomorphism. With kernel. Okay. We already talked about the fact that the kernel is precisely that intersection earlier. Now, for the second statement, we are going to reserve, as promised, I'm going to do this just for two ideals. So, suppose I1, I'm sorry, suppose I and J are co-maximal. So like I said, I'm going to only prove this in the case K equals 2, and after that it's induction. The first thing I do is I claim that I intersect J is equal to I J. And one of the reasons I'm doing this proof is to kind of recall some of this stuff. Remember, what IJ looks like is it's cracking I comes cracking J, and you've got to add them up because otherwise it's not an ideal. Let me point out that AI is an I and DI is in J. And AI, DI is in I. Why? Because I is an ideal. It's a vacuum cleaner, so it sucks stuff in. This is an I, so it sucks the BI into I. Right? But BI is in J, which is also an ideal, which also sucks things in. So this product is in the intersection. So if you have anything in I times anything in J, it's in both I and in J because the ideals suck in. So this shows that the intersection of any two ideals contains the product. Let me give you a quick example before we move on. Well, that's kind of a silly question. What happens when you take 2Z and intersect it with itself? You get the same thing, right? Anything intersected with itself is itself, right? Well, what do you suppose 2Z times 2Z is? This is 4Z. And actually, this is a strict containment, right? Because 2, the even number 2 is in this, but it's not a multiple of 4. So this is actually smaller. So I am going to prove that we've got equality here. So I guess it's going to be important that these are co-maximum. This is where I'm going to use it. Obviously, these two are not co-maximum. Now, since I and J are co-maximum, and we will use this later as well, as one. So there exists X and I, Y and J. What's that? Let A be any element of I intersect J. Multiply this equation by A. So A is in AX plus AY. Now, AX is in, well, let me point out, X is in I, and A is in J, because A is in both I and J. So this thing is in IJ, and A is in Y is in J, and A is in I, so this is also in IJ. So A, this is a product of something in J and I, this is some product of something in I and J, so this is in IJ. So if they're co-maximum, you get the other containment. Well, what it means for one to live in this ideal I plus J means that one can be written in the form something in I, something in J. Here's your something in I and something in J. Is that clear? Right, okay. Okay, so now we've got The intersection is equal to the product if they're co-maximal. Now we consider the function. F. Oh. Now consider this function here where F or is the trace of R plus I. R plus J. This is a ring homomorphism. We've already proved it here, right? Actually, we proved it earlier in the proof for a more general setting. This is a ring homomorphism. And I'll tell you something that's a little bit more surprising. It's onto, right? Why is that surprising? The reason that's surprising is, so I'll tell you why it's surprising. Actually, find R and R such that F R, R plus I, R plus J I claim that this function is actually onto it. So taking any pair of elements in R mod I plus R mod J, I can find a single R that goes here. This is a little bit surprising, I think, right? Because I'm limited to having sort of the same R here, but now I can get any pair that I want, right? That's not clear, I don't think, why I can do it. How can I use just one R to mix and match whatever I want? And the key is it's co-maximal. Since I plus J, we can find alpha and I, beta and J, such that alpha plus beta is equal to, what do I want this to be? X minus 5. Okay, now you may think that, oh my gosh, it's going completely daft here, right? Why did I pick X minus Y? Because it works and I've done the proof before, right? I mean, proofs never come out this smoothly. You always have to do some work first. Let me justify this claim. Would everybody agree that X minus Y is an element of R, right? Because both, in fact, X and Y are just two elements that live in R, right? So X minus Y is in R. So since I plus J is all of R, this X minus Y can be expressed as something from I plus something from J. Everybody okay with that? Now here's why this is important. X minus alpha. I'm going to put this on. Notice this equation gives me that x minus alpha is the same thing as y plus beta, right? Even I can get that much out. And since these two things are the same, I'm going to call them R, right? Just for giggles. Now look at f of R. This is R plus I, R plus J. But R is x minus alpha, and it's y plus beta. But alpha is in I. So this is the same thing as I. And beta is in J, so that's sucked into J. So F is on to. Because any pair is in the reach of the appropriate R. So what does that give us? Kernel of this from our previous statement is I intersect J, which is IJ, because we just proved that I intersect J and IJ are the same. So my first isomorphism theorem, rings R mod the kernel is isomorphic. And there you go. That's the Chinese remainder theorem for two ideals. Everything from now on out is just induction. It's just repeating that over and over. Any questions on it? Oh yeah, like there'll probably be another homework problem where we do this kind of thing. It's very similar to what you did in the previous homework with the order fee and stuff like that, but it's a new way of looking at it. And we're gonna look at one final type of rings before we get to the last chapter on applications, where we'll spend the last couple of weeks of the course, I guess. How many of y'all have ever read about or messed around with coding theories or been interested in it? How many of you are computer science types? I know that there's some of you out there. I know you are. So if you ever look at like coding is often done using finite fields, right? Notice that we already have a large collection of finite fields. Yeah. What do we know about Z mod P? Well, notice that the Euler phi function of P is P minus 1. That means everything between 1 and P is relatively prime to P, except everything except P itself, actually. That means that in this finite ring, 0 bar, 1 bar, all the way up P minus 1 bar, everything that's not 0 is a unit. So this is a field. Because every element in Z mod P that is not 0 bar is a unit. So that's exactly what it means to be a field when you have a commutative identity. Now, here's a little tickler. This is for next time, because we'll go through examples and then we'll probably actually start the coding next time. A field with 4 elements. It's certainly not Z4. How come Z4 is not a field? Yeah, 2 bars is problematic. Like 2 bars milk, right? So it's certainly not invertible. Is there a field of 4 elements? So here's something to think about for next time, and then we'll get on to it. See if you can find me a field with 4 elements. And see if you can find me a field with 6 elements. One of those can be done. One of them cannot be done. Let's see if you can figure out which one. Okay, any questions? Any questions? How about out there? Any questions? All right. If not, y'all have a good one, and we will see you next time.